So we're on page 419 in your workbook, and we're going to look at lesson 7, solving rational equations. So first thing that I'd like to go through with you is how we can use our graphing calculators to solve. So this is convenient when you don't need an algebraic solution, or if you're simply looking to check your work. And as well, if you don't need an exact result, that's something else that you can consider too. So solving rational equations using your graphing calculator. If we take a look at the methods, there's two methods. We've got our intersection method and our x-intercept method. So first thing that you want to do is in your graphing calculator, we want to look at this as the left side is equal to the right side, and therefore where does that happen is going to be at that intersection. So we want to graph the left side using y1 and the right side using y2 as they indicate in steps 1 and 2. Make sure that as you're entering it in the fraction in particular, that you've got brackets in the appropriate spot. So because we have a denominator that is a binomial, then we want to make sure that we enter it with parentheses around those binomial terms. If we look at number 3, it reminds us to choose an appropriate window where we can clearly see the intersection points. So always start with your standard window, and you can decide whether or not that will be sufficient. If you need to adjust, certainly adjust from there. So then we'll use the intersect feature. So let's take a look then. Try to hit pause, try to enter those into your calculator as y1 and y2, and then come back when you've got that complete. So you can see that we've got y1 is equal to that left side. I've got the parentheses around the binomial terms. y2 is equal to the right side. So if we go ahead and graph that, to me this is actually quite clear the way that it is in our standard window settings, going from -10 to +10 on both the x and the y axes. So I'm going to leave it at that. And at this point, then we want to go to the intersect function. So is with second trace or calculate, and you'll see the intersect at 5. So you can either scroll down or just hit 5. And so what this is looking for is simply which two curves do we want. The blue one is what I have in y1. If I want to see what's in y2, then I use the up and down. To move the cursor, we'll use the left and right. So I just want the cursor basically to be close to the intersection point that I want, and between those two curves that I want, y1 and y2. So I got that. And then the second one is close. So take a guess. Yes, please. And there it is. So the intersection is at y equals 2, and the x value is at we're looking at scientific notation here, and so that is at x is equal to 0, because essentially we're talking about 3.864 times 10 to the -15th. So there's a lot of zeros before that, so we'll take that to be x is 0 and y is equal to 2. So the second point will be here, so let's take a look at that. So second, calculate or trace, again, fifth option, and the first curve, so we want to move this closer to that intersection point. So there we have it. And then again, there it is on y2 is equal to 2, close to that intersection point. Take a guess. Yes. And so when y is 2, x is 2 as well. So these end up being both nice integer values in terms of where my x intersect, those intersection features are. So the x coordinates are then x is equal to 0 and x is equal to 2. So if you wanted to draw that out, that. And our other graph is right here. And so there's one point at x is equal to 0, and there's a second point right there. Okay. So moving on to the x-intercept method, it's essentially what we've done previously, which is to set the right side or the left side to 0. So if we set the one side to 0 by subtracting 2, then we just graph the one side, and then now you're solving for, rather than the intersection point, you're solving for x, which is essentially looking for your x-intercepts. Okay, so take a moment, hit pause, enter that graph in to your calculators then. So what you can see then is I've left the other two in there just so that you can see what the calculator is doing when it's graphing it, and I've entered in the one side 3 over x plus 1 over x minus 2 in y3, so that'll be graphed as a black curve then. And so if we take a look at the graph, then there that is. So what does it do is it essentially just shifted everything down 2 units. And so clearly we can see right here that intersection with y equals 2 is exactly the same spot as where it intersects the x-axis. Same thing, that intersection with the y equals 2 line where the blue and the red intersect is exactly the same point as where the black curve is intersecting the x-intercept. So again, to solve in this particular case, using our calculator, we can do second calculate, and we're looking for the x-intercepts, which are also the zeros, and so then it's looking for left. So being careful right here, what are we looking for is we're not looking for the x-intercepts for the blue, we're looking for the black. So we need to scroll, use the down to get to y3, which is looking at black, and we want to go to the left of that x-intercept, which is there, and then scroll to the right to get to the right of that black, where that black curve intersects the x-axis. And so now it's saying take a guess at the x-intercept that is between these two boundaries that we've set out, those two dotted lines, and we'll hit enter, and there's that x-intercept. So again, let's find the other one. And so it's calculate the 0. And so again, it's reverted back to our first function. So we want to go scroll down to y3, and we want to make sure that we are to the left of that x-intercept. And so, whoops, I've just dipped below. So now I am to the left of this x-intercept right here. So we'll hit enter, and we'll scroll to the right to get to the right of that x-intercept and hit enter. And so again, we're going to ask the calculator to find this x-intercept, which is between the two boundaries that we've set out, and hit enter. And of course, it is x equals 2. Okay. So again, x equals 0 and 2. So let's look at how we can solve those algebraically then. So in terms of solving rational equations algebraically, what we are looking for really is to try to eliminate the denominators as soon as possible. So a lot of people look at, there are methods to find a common denominator and then look at removing the denominators, but it's a lot easier to get rid of the denominators right away, and you see that they are multiplying each term in the equation by the lowest common multiple of the denominators, which is essentially the lowest common denominator. Okay, so let's take a look here. So we've got 4 plus 2 over x is equal to 7 plus 3 over x. So our common denominator would be x. So I'm going to multiply each term by x. And so that will essentially give us 4x plus 2, because the x over x is just 1, is then equal to 7x plus 3. Again, the x over x is just 1, so that comes back to a really, really simple linear equation for us to solve then. And so moving your variable, isolating that onto one side, and moving your values to the other side. So then I've got negative 3x is equal to 1, and x is equal to negative 1/3. To verify the solution, of course, we can substitute. We can do a left side, right side check to algebraically verify the solutions. But it is also important, of course, to state your non-permissible values because the issue is that if our solution ends up being a non-permissible value, then we would have no actual solution. The solution would not exist. So x cannot equal, or non-permissible would be x cannot equal 0. Okay, so if we check, we've got the left side is equal to 4 plus 2 over x, so 2 divided by negative 1/3, or 4 plus 2 times negative 3 over 1. So 4 minus 6, which is negative 2. On the right side, we've got 7 plus 3 divided by negative 1/3, or 7 plus 3 times negative 3, or 7 minus 9, which is also negative 2. So left side is equal to right side, so we know that we've done this correctly then. Looking at b, so again, to get rid of this denominator, I want to multiply the left side by x plus 1, but if I'm multiplying the left side by x plus 1, then I will also multiply the right side by x plus 1. To get rid of this denominator of x plus 2, I need to multiply the right side by x plus 2, therefore we'll also multiply the left side by x plus 2. So the x plus 1 over x plus 1 cancel on the left, the x plus 2 and x plus 2 cancel on the right. So I'm left simply then with 5 times x plus 2 is equal to 2 times x plus 1. So simply distribute and solve. So take a moment, hit pause, and come back to it when you've completed it, please. So if we take a look, we should have ended up with a solution x is equal to negative 8/3, and then we need to go through our restrictions to make sure that our solution is not one of our restricted values, to ensure that it is a possible solution. Then we will verify by substituting in our solution into the left side and the right side to ensure that left side equals the right side. And it does, so everything is good, and our solution is x equals negative 8/3. Let's take a look at the next example. So solving then again, what we recognize then is that if we have just a fraction equal to a fraction, because when we go and we multiply this side by 2x plus 3, these ones cancel out. I'm multiplying the right side also by 2x plus 3, then we need to multiply the right side by 3x plus 5. That takes away that denominator, and we also, of course, need to multiply the left side by 3x plus 5. So when it comes down to it, what do we have is 3x plus 5 times 4x minus 2 is equal to 6x minus 1 times 2x plus 3. And so when people say, hey, you can just cross multiply, the cross products are equal. So when we have a proportion, which is a fraction equal to a fraction, or a ratio equal to a ratio, cross products are equal. And that's what works right here. You can see, which is 4x minus 2 times 3x plus 5 is equal to 2x plus 3 times 6x minus 1. And the reason that works is because we're multiplying both sides by the denominators of the common denominators, eliminating their own denominator. So cross products are equal, but we can only do that when we have a fraction equal to another fraction. If there's extra pieces, then it's not going to work. Okay, so taking a look at this, now all we need to do is expand and solve. We may end up with a quadratic, in which case you guys know how to solve quadratic equations, so either through factoring or quadratic formula. So let's take a look at times, of course, the x squared coefficients may eliminate the x squared, so leaving you with a linear equation instead of a quadratic equation. But we shall see. Don't forget about your non-permissible values. So hit pause and complete that solution, please. So working through that solution, it was nice that the 12x squared eliminated itself, so leaving us with a very simple linear equation, and therefore x was equal to -7/2. We had to go through our non-permissible values to check that we didn't have a conflict between our solution and our non-permissible values. Okay, so x is equal to then -7/2. So taking a look at B, we have the binomial denominators of t plus 1 and t minus 3. Everything is in factored form, so we need to get rid of those denominators. We'll multiply everything by t plus 3 and t minus 3. So let's take a look. So if we multiply this first one by t plus 1 and t minus 3, second one by t plus 1 and t minus 3. And of course, if you're doing it to the left side, we need to do that to the right side as well. T plus 1 times t minus 3. T plus 1s in that first term will cancel each other out. T minus 3 in the second term will cancel each other out. So again, we are left without a denominator, which is what we want. So our new and improved equation is 5t minus 2 times t minus 3 minus 2t minus 1 times t plus 1 is equal to 3 times t plus 1 times t minus 3. So at this point, we know that we just have to expand the binomial multiplication. Be careful right here with the subtraction. So you want to apply the negative into the product. So keep parentheses on your product. With 3 times the binomials, I would again recommend that you multiply the binomials first, then distribute the 3. So again, hit pause and go through the solution and come back and check your work. So working through the solution, we should have found then again conveniently our t squared canceled each other out. So we're left with a nice simple linear equation that solves itself to t equals 4/3. Checking again with our non-permissible values. The denominators cannot equal 0, so our non-permissible values are t cannot equal -1 or +3. There's no conflict with the solution, so our solution stands as t equals 4/3. Excellent. So let's take a look at the next question then. In this particular case, what do we want to do is we can see that x squared minus 16 can be factored, and that will help to simplify things as well. So go ahead and factor that and try that solution, and it works itself out quite nicely. It doesn't ask you to state the non-permissible values, but I would always include that to know whether or not your solution actually stands. So again, please hit pause and work through your solution, and you can come back and check your answer. Okay, so taking a look, we've factored the difference of squares to x plus 4, x minus 4, so we recognize that that would be the least common denominator. So we multiply each term by x plus 4, x minus 4, which allows us to remove all the denominators, and we end up with a really simple linear equation that we can solve, and x equals to 3. Check our non-permissible values with our denominators and looking specifically at the factored form, and x cannot equal 4 or -4, which doesn't interfere with our solution. So, would you please go ahead and complete the assigned workbook questions? Let me know if you have any questions.